To explain the file sharing semantics in a distributed file system, let's see what these look like first in a single node environment and then compare how they differ from the distributed multi-node environment. On a single node in a Unix environment, we have the following semantics. Whenever a file is modified by any process, in this case, process A writes C, that change will immediately be visible by any other process on that machine. So process B will immediately see that C. When it performs a read on this file, we'll get ABC. This will be the case even if the change isn't actually pushed out to disk, because both of these processes have access to the same buffer cache. In distributed file systems, that's not the case. Even if the fact that process A performed an update, wrote C to this file, gets pushed to the file server immediately, that message, it may take some time before that message actually arrives here. So it is possible for process B to not be able to see that message for a while, and whenever it performs a read operation on that file, even in that period after this file was written to, it will continue seeing that the file consists of only the elements A and B. Given that message latencies may vary, we have no way of determining how much should we delay every possible read operation in order to make sure that any write that may have happened anywhere in the system arrives to the file server so that we can guarantee that this process B does read the most recent version of the file. So in order to maintain acceptable performance, distributed systems would typically sacrifice some of the consistency, and they will accept some more relaxed file sharing semantics. Let's see what are some possible meaningful file sharing semantics for distributed file systems. As a baseline, we will contrast this to the case when the file system is on the single machine where every write is immediately visible, and this is what's referred to as Unix semantics. Something that makes sense to do is to enforce what we call session semantics. Whenever a file is closed, the client writes back to the server all of the changes that it has applied to that file in its cache. Whenever a client needs to open a file, it doesn't use the cache contents, instead goes and checks with the file server whether or not there is a more recent version of that file. We call this session semantics, with the period between the file open and the file close being referred to as one session. With session semantics, it is very possible for one client to be reading a stale version of a file, while another client is either updating that file or even reading a more recent version of the file. But at least by knowing that when we open or when we close the file, we will be consistent with the rest of the file system at that particular moment, we can reason something about what kind of sharing guarantees do we have when we run in this type of distributed file system. Although session semantics are intuitive to reason about, they're really not good for situations when clients want to concurrently share a file, write to it and see each other's updates, that have to open it and close it repeatedly. And also when files stay open or are being updated for long periods of time, these can result in long periods of inconsistency in the file system. For that reason, it makes sense to introduce some time intervals when these updates happen. With introducing time intervals, the client updates, writes, will be propagated to the server periodically. One way to think about this is that the client has some sort of leash on how long they can use the cache data. However, in this case, note that we don't really mean that it's an exclusive lease like locking. This is a completely separate issue. In the same way, the server notifications, the invalidations, are also periodically sent out to the clients. This can establish some sort of time bounds during which the system can potentially be inconsistent. So at least if there are any conflicts, it will be easier to correct for them. There will be likely fewer of them that have accumulated during the periods of these updates. Since the client doesn't really have any idea about what are the start and the end times of these synchronization periods, the file system can also provide some explicit operations to let the client flush its updates to the remote server, just like what we do with flushing the updates to disk when it comes to local storage, and also to explicitly sync its state with that of the remote server. Again, these types of operations are not necessarily distributed file system specific. They're used in regular local file systems as well. Other file sharing policies also exist and make sense for certain situations. For instance, files may be simply immutable. You never really modify a file. You simply delete it or you create a new file with a new name. When you're sharing photos via Instagram or Facebook, you don't really upload a photo and then go and edit it. If you need to change the photo, you change the photo and you upload the modified photo. These types of distributed storage have these kinds of semantics, immutable files. Another useful file sharing semantics would be for the file system to provide transactional guarantees. What this would mean is that the file system will need to export some interfaces, some API, so that the clients can specify what is the collection of files or the collection of operations that need to be treated like a single transaction. And then the file system can make some guarantees that all those changes are atomically committed, atomically made visible into the file system. As we work through the rest of the lesson, we will look at what are some of the file sharing semantics that are supported in some distributed file systems, and also what are the mechanisms that are required to achieve these types of semantics.